Lecture number 29. And today is again date 12/04/2021. Let us understand what do you mean by second moment of area. We have understood first moment of area and its application is to locate centroid of a given composite area. Now second moment of area means what and what is its physical application, that you have to see. So you are going to solve some problems in strength of material where you would have a beam supported on a simple support. That means one side hinge, other side roller would be typically represented. If you look at this beam section, that beam section can be of I section or T sections like this. Say this is of T section, like this, or it can be of rectangular section for simplicity. So this beam can be of rectangular section, of T section, or it can be of L section, and so on. So here something called the neutral axis. So what is neutral axis is that one passes through the centroid of the section. So this is what is called the neutral axis. So this should be same if the section is rectangular section. For the simplicity, if I look at from here, so this is my neutral axis. This is my neutral axis of the section, right? So I have to see that the second moment of area is important. If I have here load acting at the mid span, or there is a load given which is the UDL, uniformly distributed load, right? Or it can also be acted upon with the couple moment. So if you are given with a couple moment like this, so this is under loading, what would happen? This would be under bending. So if we have a pure bending equation, that means you do not have lateral load, you have only the couple moment, right? If you have a couple moment, then there is something called the bending equation, and that bending equation is going to give you what is the stress developed in the section. The stress developed in the section, if you look at, if you consider horizontal lines in these beams or the layers, horizontal layers, so below the neutral axis, those layers, so this is one layer, second layer, third layer, like that, and above the neutral axis I have number of layers stacked like that if I assume. Then the bottom layer and the layers below the neutral axis would be under pull, under tension, whereas the top layers would be under the compression. If I have bending, if this beam is subjected to a pure bending like this, bending moment given like this, right? So what would happen at that time? I have my bending equation called the M, total bending moment, by second moment of area is what is same as sigma by Y, what is same as E by R. So this is what is something called pure bending equation. Pure bending equation. So there are some assumption theory of pure bending that we will study in detail. I'm not going to go more details now of bending equation. How can you derive this? Instead, I am just putting this now for your understanding what is called the pure bending equation. So in this, if you look at the bending stress that is developed here, which is sigma, is given by M into Y by I, where M is the total bending moment in the section, Y is the distance of the layer that I consider. So here I said this layer. So if it is bottommost layer from the neutral axis, it is at a distance d by 2. If depth is d for the section, at a distance d by 2, bottom layer, I have to get what is the bending stress. So if I say that the distribution of this bending stress for a rectangular section, if you look at, it would be a linear distribution. So you would see that At the mid span, at neutral axis, there is no bending stress. Whereas at the bottom, you would see that is maximum. At the top, it is maximum. So here it is tensile nature, and here it is compressive nature. So above this, it is compressive nature. Below this, it is tensile nature. So the distribution is like this linear distribution. So at the neutral axis position, there is no stress, whereas you see that bending stress given by my by I is having its value maximum at a distance y is equal to d by 2. So this is all something that you will study. And to get this bending moment at any section, if bending is not pure bending, non-uniform bending, that means you will have a couple acting like this shown and the UDL and some concentrated load at different spans length. Then it is something called non-uniform bending of the beams. So still you can draw a bending moment diagram for that, and as the span, along the span, every section what is the value of bending moment you'll know. So the section consider, you know what is the bending moment, and you know the layer, what is that, you look at it, and I of the section. So I of the section in this case throughout this length is constants, that is this section, that will not change. So now you see that the bending stress would be less if I have more I value. So the bending stress is less if I value is more, right? So I value about what? About if this is my XC axis and this is my YC axis, centroidal axis of my rectangular section, this is going to be IXC. IXC. So if IXC value is more, I would obviously have less bending stress. So what do you mean by that? The beam can support more bending load. That can be easily proved with a simple test that you take a scale. So you have thin scale. Width of the scale is this much. So if you have orientation of that in this way, you can't bend it. Whereas if you have flat surface seen upward, and then you can easily bend. So reason is what? When you have got a scale held vertically up, the depth will be more, whereas in the other way, the depth is very, very negligible. So if you have more depth, you would have more second moment of area. That is what you would understand. More second moment of area. Otherwise, it is called area moment of inertia. So second moment of area. Otherwise, it's called area moment of inertia. Right? So this is what you should find out. So now the task is how do you find this second moment of area of the composite area section given. So what do I mean by composite area? If I take a rectangular section of the beam, it is standard area. If I take T section, it is composite area because it is made of two rectangles. If I take L section, it is made of two sections, two rectangles. If I have I section, then it will be made of three rectangles. So that is what is called a composite section. So you should understand how do you find out moment of inertia of the composite section, right? So for that, let me just take a problem and explain you through that problem what all that you have to understand as far as this topic is concerned, and that will help you to go through additional problems from the textbook, right? So let us take a simple I section. Okay, let me just give you this problem. So consider now, instead of I section, let us take simplicity T section. So you understand now what I mean by section, right? T section can be a section of a beam. So this is the section. So it is composed of two rectangles, and by symmetry I can say that is axis of symmetry. It has got an axis of symmetry. So this axis will be my YC axis. What is my XC axis? How do I get? For that I should have my reference. So reference, I take it this point. So from this base, where is my Y bar located? That's my XC axis. So I will have my centroidal axis, or that is my neutral axis of the section, right? So how do I get that? for that first moment principle that you have to use. So I have now in this case x bar is 0. So that is why I have this yc. X bar 0 I write by symmetry. Now what is my y bar? So y bar would be sigma ai yi by total area. So it is a1 y1 plus a2 y2 by total area. What we have done just in the previous problem. So now what is a1 for that? Let us take this dimension. So this is 25 mm and this entire length is 100. Similarly, this one, this depth from here 75 mm and this is 25 mm. This is 25 mm. So this is section geometry, right? So if I have this section geometry, I would be able to now work out what is my y bar. So my first rectangle is here located. From point O, where is it located? Here. So what is the centroid of that individual? So this is my x1 and yc axis, what is y1 also. So this is my xc1 axis. I would get that by the distance y1, right? And for the second, this area, this height is 75. So where will I get midpoint of that? So that will be somewhere here. So that is my xc2 axis, and this distance is what is my y2. So now I would be able to get this. So what is my a1? Area is 25 by 100 plus a2, into 25 by 100 is the area, multiply that with the y1. So y1 is from here. So this height is 75 plus this half the height of this 25. So that would be 75 plus 12.5 is what is y1 plus what is a2? A2 is 25 by 75. Multiply that by 75 by 2, that is 37.5. Now divide this by total area, that is 2500 plus 25 into 75. That's total area. So let us just calculate this. What is that we get? So what is in the numerator? It is first moment. What is in denominator is the total area. So that gives you y bar. So first moment about x-axis is what I am calculating. So I'm 2500 into 75 plus 12.5 is in bracket is 218750 plus 25 into 75 into 37.5 is 70312.5 divided by 25 into 75 plus 2500. Total area 4375. So I will get this 218750 plus 70312.5. So which is comes out to be 289062.5 by 34375. So y bar value we divided by 4375, which is 66.1 mm. So what I mean by that is I have my centroidal y-axis, yc axis from the base at a distance 66.1. So this is my xc axis, whereas this is my YC axis, vertical axis, and this is centroid of my T section. So now I have to get about this XC axis, what is my second moment of area. So for that, let us define now what is second moment of area, right? So we need to understand what is second moment of area, right? So let us take now a rectangle for that purpose, right? I'm going to just teach you what is second moment of area, and then we will get back to this problem again, and you will understand how do you go about solving, right? So what is second moment of area? I have now, for example, look at a rectangular area, as this is required for this problem case. So I have a rectangle where this is of width B and depth D, and this is by looking at this geometry, I can say by symmetricity my centroidal axis are this. These are my centroidal axis. This is XC and this is YC, right? So now, how do I get for this? Let us understand. First, let me just consider an elemental area, because I wanted a second moment of area. So let me consider an elemental area. At a distance y with the width of the area dy. So what is the dA of the area? What is dA of this area? Width is b and dy. So b dy is what is dA of this area. So now the definition of first moment of area about XC axis, IXC, would be integral y squared dA. Y squared dA. Remember that we had QX is first moment. How did you get? That is y bar into total area, which is defined as y dA. So integral y dA is what is first moment of area. Integral y squared dA is what is second moment of area. And this integration goes from y varies from this point to that. So here it is minus d by 2 to plus d by 2, right? So this is minus d by 2 to plus d by 2. So this is the definition of second moment of area. So how do I get that? Now see, this is going to be integral y squared dA is b into dy. So b is constant. I take that out into dA. So I would have this is minus d by 2 to d by 2. So that's going to be b into y cube by 3 minus d by 2 to plus d by 2. So what is that I have? So this would be equal to b into, when I substitute that here, b by 3 let me take out. When I substitute that, it is d cube by 8, d cube by 8 minus of minus become plus d cube by 8. So that's going to be 2b d cube by 24. That's going to be b d cube by 12 is what is IXC. So one can also derive for IYC. In this case, bending is with respect to XC axis. So for solving this above problem, IXC is sufficient. This is sufficient. But here I require to find formula. Supposing similarly you want to get IYC, you can get that considering an elemental area, vertical strip at a distance x with dx, and follow this principle of x squared dA, and that would result in b cube d by 12 is what is IYC. One can prove. But now this formula is not required for the T section that we are considered, but whereas this formula is very much essential. So this formula is what with respect to my YC axis, so my XC axis, centroidal axis. But now see, when I have a composite area, combination of two rectangles, my central axis is here, XC, right? I know for an individual rectangle, my centroidal horizontal axis. What is it? XC1 and XC2. But when I see that as a composite section, T section, I have my new centroidal axis XC. So about this I want to get. So how do I get this? Is through a theorem called parallel axis theorem. So you have to understand one theorem at this point of time. This is what is called the parallel axis theorem. So what do you mean by parallel axis theorem? If I have to find out at any of the given x-axis which is parallel to the centroidal axis, that would be same as Ixg plus area into dy square, d subscript y square. So what is dy? Is the distance, parallel distance between two horizontal lines. So this is the formula. We can have a proof for this, simple proof for this. At the moment, okay, let me just explain you that proof as well. Let us consider this is my x-axis, this is my y-axis. Let me consider an arbitrary area. So this is an elemental area in this, which is dA, right? I know for this centroidal axis, by applying first moment principle, that happens to be its centroidal point. So this is my XC axis and this is my YC axis. YC axis. And now this is located where this is located from XC YC axis where this element, what is the distance that you say? That is x comma y distance. So let us say this is x and this is y distance from here. Whereas my YC axis located from y axis reference where it is, if you have understood first moment principle, that is x bar, right? You locate this AG, how? By finding x bar and y bar. So this distance is y bar. This distance is y bar, right? So if I have this elemental area, I go with my definition of Ix equals integral y squared dA, right? So y squared dA, so that's going to be integral here this y is what? Y bar plus y. It is not simple. So I am not doing with Ixc. I wanted about this x-axis. So that means this distance, the elemental area located from here, what distance? Y bar plus y distance. So that is y bar plus y, there is y bar plus y squared dA. Right, so there is some slipping. Yeah, so this is that area. Right, if we have a next class, we can proceed. I'll just finish later on. You can revisit this lecture. So now y bar plus y, if I expand this, it is integral y bar square plus y square. Why it's not writing y square plus 2. So there's some issue with my pad. So 2y bar into dA, right? Into dA. Just a minute. Yeah. So now see, let me just split these terms. So it is going to be integral y bar square dA plus integral y square dA plus 2 integral 2y bar is constant to y dA, right? So now what is integral y dA? That is its first moment. So first moment about the centroidal axis is what is equal to 0. That is to be understood. So that is what is defining axis of symmetry. So when I have a rectangular section, first moment about axis of symmetry is 0. You are saying that is because it is about centroidal axis. So I have this area, this elemental area dA here. So if I do y dA about xc axis, that's 0, or x dA about this is 0, then only I'll get to this point location. So x comma y is 0 for this given section about xc and yc axis. That refer to first moment of area about centroidal axis is 0. So this term is 0. So here you see integral y square dA is what? Ixg. Integral y square dA, this is Ixg, right? So let us say this is from here y dash distance, to avoid confusion. This is y dash distance, Ix to get, right? So here integral y square dA is what is Ixg, Ixc or Ixg, right? Ixc, I can say Ixc about this point. And what is y bar squared? Y bar is the distance between this parallel axis. See, this y bar is, I have this x axis. About this axis only I am writing it. What is that I write is Ix is about this reference axis. What is this distance? This distance is y dash. So I have here y dash squared dA is by definition. So y dash is defined by y plus y bar. So that is what I substituted here. So now this has become Ixc, this is y square dA, because see this is y square dA is about this, so that is its second moment of area. And here y bar square, y bar is now this distance. So y bar here is what is now dy that I talk. So dy, distance between, parallel distance between these two horizontal x and xc axis. That is y bar. So y bar here is what is d subscript y, distance along y axis between x and xc axis, that is dy. So I can take that dy square integral dA. So integral dA is total area. So I will take this term first, Ixc plus total area into dy square is what is Ix. So this is what is parallel axis theorem. True. So that is what I have explained you here. So that's what I have written here. Ixc you can write, or Ixg. Some books it is written G, some books it is this. So about centroidal axis, if I know moment of inertia, I can find it about any parallel axis by applying parallel axis theorem. So that you have understood. If that is so, now I can quickly find out for this T section my second moment of area, right? So how do you get now for this T section? Second moment of area. So this is given section. This is 100. This is 25. And again I have it here. This is 75. Height, and this is 25, right? This is given. So I have now one axis of symmetry, that is YC axis, sorry, vertical line, YC axis. And the XC axis. This is XC, XC, this is YC axis with respect to base, right? Okay, so now my what is that I needed is IXC of this I needed, right? So how do I get that? Is simply by IXC. I have got now centroid, right? So I can get that like this. The simple way is using parallel axis theorem, I can write it like this. So I wanted XC and I can get all about this x-axis. So IX would be IXC plus area into this distance. So this distance dy would be here y bar square, right? So this is that. So in this y bar just now we have found, which is 66 point. What is the value we got? 66.1 mm. 66.1 mm is what is y bar. The total area I just have calculated, that is in this denominator 4375 centimeter square or mm square. 4375 mm square. This is an mm. So IXC I have to get. That IXC would be IX minus area into y bar square. So I write it in this way. Right? I write it in this way. So now see that this formula what we had here, we derived about IXC axis, which is centroidal axis here. So if I have to get about the base with respect to base x-axis, I can apply here as well my transfer theorem, right? So what does my Ix? It is IXC plus area into y bar square. So if I apply that, it is BD cube by 12 plus BD is this, and y bar is D by 2 square. So if I work out this, BD cube by 12 plus BD cube by 4. That's going to be BD cube by 3 is what is Ix. So if it is for the base, with respect to base, I have to get second moment of area. It is BD cube by 3. I can also get through integration, or I use here the parallel axis theorem, because I have derived about XC axis this formula BD cube by 12, and that plus area into this distance D by 2 square. If I put, I should get. So this is my formula that I know. So now continue working on this T section. Ix is for the entire T section about x-axis, right? So how do I get now IXC is from this. So let me first get Ix for this T section. That would be Ix1 plus Ix2. What is Ix1 plus Ix2? 1 is this area, 2 is this area. So when I say Ix1, that is Ixc1 plus A1 dy1 square plus Ixc2 plus A2 dy2 square, right? So what is Ixc1 is what is its individual centroidal axis. So this is Xc1 axis, and this is Xc2 axis. So now I have to get for the first rectangle about x-axis means Ixc1 I should know plus parallel axis theorem. So if I do that, it is what BD cube by 12. So B is 25 into 75 cube by 12 plus area 25 into 75 into d by 1. So d by 1 is this distance. This is d by 1. So that's going to be 37.5. So into 37.5 square. So this is all first one plus second bracket Ixc2. So Ixc2 means what is that? You look at it here is about this XC axis, about this XC axis. So that would be base is 100, D is 25 cube by 12 plus 25 into 100 is area into, in place of this dy1, so what is dy2? dy2 is from here again. This is dy2. The distance of x-axis, the distance between x-axis and xc2 axis. So this is dy2. So how much is that? 75 plus 12.5. So that is going to be 87.5. So 87.5 square, right? So 2.5 is 77.5, 87.5 square. So this is what is my Ix. So by adding these two, I get some number value, and that unit would be what? Mm power 4, whatever that I get. And then I can go in for finding Ixc about this axis. What is that I needed from this formula? So I can use then this formula, get Ixc. So Ixc for the composite area about its own centroidal axis would be Ix, what you have got it here, minus total area of this composite into into y bar square. Y bar is now this is y bar. So this is y bar. Y bar, which we have calculated as 66.1, right? Into y bar square. So you can find out using this. See, such an interesting problem. There is so much of involved geometrical understanding required, mathematical definition, formula definition required, and so on. So it is a simple rectangular section, and you can calculate from this. I leave it to you as a homework. So work out this and get Ix value and substitute that here, and total area and y bar values are given here. See, these are the values given. Substitute them in this formula. Finally get your Ixc. So I leave it to you as homework to complete, and this is all what is called the second moment of area, and it's important, right? If you have any doubts, I would answer. Otherwise, we will stop at this point of time. Any doubts, anybody? If you do not have any doubts, let me stop recording.